asked us this by. So this was the working principle of galvanism, right? Right,
Yes,
Arjun?
sir.
And yeah, so let me. So if what would be the current if I calculate the current? So what would be that? Right. This is so phi is what? So deflection angle is phi. This is the deflection, and this is NIAB by K. This is the deflection. So if you calculate I, right? If you calculate I, what would be that? So current would be what?
So current would be
So then current would be what? Current would be I, and you take all these things in the other side. So phi, K, and this divided by N, and I and A, so NAB, right? This is N, A, and B. So this is the current, right? And if you calculate the division of this thing, right? So if you calculate phi by I, right, you have this deflection angle, and what would be phi by I? So this would be NAB by K, right? Clear?
yes. Wait, sir.
Is it?
One second,
Yeah,
sir. Current
it's
I is equal to phi k by NAB.
yeah,
So phi by I is equal to sir house.
yeah. So from here, right?
Oh
I
yeah, yeah.
take this I, I take this I in this side, right? And then this
Mm-hmm.
would be the. So this is
Yes.
called the current sensitivity, right?
Okay, sir.
This is called current sensitivity, right? And then you have, so let's say if I multiply this by, uh, right, so in the right hand side, again, let me just write this thing. Phi is NIAB by K, right? So I want to calculate, I want to calculate voltage from this thing, right? So what is the relation between current and voltage? What is the relation? Yes, Ohm's law. P is IR. So I would be how much? I would be how much?
So V is equal to, oh, sir. I is equal to V by R.
IR. So if we put this value in here, so NAB by K and V by R, right? This is phi.
Yes, sir.
So if we take this V, right? If we take this V the other side, so what will we get? This is phi by V, and this is NAB by KR. So this is what we call the voltage
Yes, sir.
sensitivity. So these are the two sensitivity that we have. Uh, this is is 5 by V voltage sensitivity, and then you have the thing that I want to talk. And yeah, and then how can we convert the galvanometer into an voltmeter, right? So how can we do that? So I will directly write, right? I will directly write a scenario to conversion of galvanometer into an ammeter. So how do we do that? The idea is that we connect a shunt resistor in parallel, make an ammeter. Right. So let's say you have this galvanometer and it has some resistance, right? And yeah, let's say that you have this galvanometer and this has some resistance, let's say Rg. And then you apply and then you connect, right? You connect a shunt resistor parallel to this thing. So this is your shunt resistance. And then this whole thing is now called a diameter, right? This whole thing. I should write it in this, right? So I should write it. This is the resistance, and this is your G. This is RG, and the current which is flowing, that is IG, right? And then you have this current. So let's say I current is going inside. So this is IG. What would be this current? Yeah, junction 2.
Yes,
So
sir.
what would be this current?
That would be I.
Okay, so I current is going inside and then outgoing. These are outgoing at this junction, right? So one is incoming and then two are outgoing. So this plus this would be I, right? If you have, let's say, this is the junction, right? So
So you're
if
talking
you
about the
have,
junction rule, right?
yeah, so I'm talking about this junction. Let's say this is I1 current going. Then this is I2, this is I3. So at this junction, this is incoming, right?
Yes,
At
sir.
this junction, these are outgoing. So the junction rule says that incoming current, that is I equal to outgoing. So I1 would be equal to
I2
I2
plus
plus
I3.
I3. So
Yes, sir.
I
But
would be
for
equal
this
to
one,
IG plus X.
I.
Yeah, so
But
this one
sir,
would
I
be
thought the
I
whole
minus
junction
X.
rule stuff applied only when
Yeah,
the current was like kind of the current was like preceding both of these. I didn't know it was like this that would be in front of it.
pre-
I thought it should precede it, like be before it.
preceding, lagging, and all those things comes in the AC part, right? Alternating current. So they are in the same phase, right? These are all uh, these are all direct current devices, right? We are talking about the cells, batteries. So those are DC. They are not lagging. They are not preceding, right? They are in the same phase. Yeah, so am I saying the same thing or are we in the same page? What do you mean by preceding?
No, sir. I thought that the I must be like
Yes,
before it in the sense, like how you made on the second one, sir.
second one. Yeah, this one. Yeah, so I can draw this one as this as well. Right. I can draw this diagram in this way as well. Right. So at this point, this one is incoming. These two are out. Same thing. Okay, clear.
Yes, sir.
Is it clear? Okay, so then what is this shunt resistance, right? How can we calculate this shunt resistance? So we see that these two are parallel with each other, right? So voltage on this thing would be equal to V1 would be equal to V2. What is the voltage in this device? What is the voltage? What is voltage? Voltage is IR,
Yes,
right?
sir.
So voltage in this one is IG and RG,
Yes, sir.
right? What is the voltage in this thing? That is I minus IG, right?
Into us.
So if we can, yeah, so this is the resistance, this is the current. So this would be the voltage. Then if we calculate S, so S is simply IG by I minus IG and then RG. This is how you calculate the shunt resistance, right? Remember, remember the shunt resistance is very small. So S is very, very less than G, the resistance in the calculation. So this is how you make the ammeter, right? And then how do you make then the next step is the conversion of galvanometer how do we do that? So you add add load resistance of greater value of high value in series. Yeah. Right. So in this one, what do you do? I have this galvanometer which has some resistance, right? And let's say the resistance is and then which is on, right? So then this whole thing is your volt. Then this is your right. This is, okay, and you can see that the whatever the current is passing through. So I would be how much, right? This would be, let's say this is voltage. So voltage is I and R plus RG, right? So you can calculate. So you can calculate this R which is V minus I by RG. So this is how you calculate this load. So this is all about the galvanometer, ammeter, and the current and voltage sensitivity. Is it clear to you? Is it clear?
Yes, sir.
Then please note it down. Please note that. So that is all about this chapter.
Yes, sir. Done.
Done. And yeah, we can do this problem. We can do this NCERT sample question. And so we can this problem. So let us do this problem. Oh, but first you have to note it. So first, this whole thing is yours. So this whole thing is your ammeter. Note it down, and then we'll do one question that is very important, and then we'll yeah, move on to this next chapter. Whenever you have admitted it, down.
Yes, yes. One more minute. Okay, sir. Done.
Done. Okay, so then let us, yeah, this part you also noted it, right? This thing you also noted, right?
Yes, sir.
Then let us do this problem, and then you will see that how the shunt resistance or how these load resistance are important. Because we have seen that we cannot directly use galvanometer as ammeter or voltmeter. We cannot directly use. We have to connect a shunt resistance or we have to calculate connect a load resistance to it to make a voltmeter or a ammeter, right? So let's see that why we do that. Okay. The question is that you have, and this is the example 4.13. So in this example, they have on an ammeter, right? And this is This is 3 ohm resistance, right? And then it is connected with uh, 3 volt supply, right? So the ideal condition is what? What is the ideal condition if you don't know about this ammeter? So what should be the current which should be flowing through this circuit? What should be the current reading that you should get? What should be the current reading that you should get? Forget about this ammeter, right? So if you have this thing, so what should be the, let's say this is 3 volt, this is 3. So what should be the current reading that you should get? Yeah,
Hmm. I is equal to V into R, right?
okay. E is IR, so I is V by.
V by R, yes, sir, V by R.
So 3 by 3. So ideal case is that you get a 1 ampere of reading, right? This is the
Yes, sir.
ideal case. That you have this resistance, you have this voltage, and when you measure with some instrument, so the ideal thing is that you should get 1.
Yes, sir. Sir, sir, I can't hear you. Hello, sir.
Right. That is the ideal case. Yeah, what are you saying? Yes, yes.
Hello, sir. No, sir,
Yeah.
sorry, sir. Can you
Yes,
just
yes.
repeat what you said, sir? I couldn't really hear you.
Yeah, I'm saying that the ideal scenario is that the reading of current disconnect. Yeah. So the ideal scenario is that the reading of the current which should, so right, Arsalan, did you hear what I'm saying? Yes, did you hear what I was uh,
Hello, sir.
Arsalan? Yes, Arsalan, can you hear? So yeah, did you understand what I was saying?
No, sir, sorry, sir. I don't know why. I
Yes,
think my Ethernet, I think so, might have gotten loose. My wired connection got loose, and why I just. Sir, can you hear me?
yeah, you are. Yeah, please, okay, please check that. Yeah, yeah, I can hear you. Yes, I can. Yes, I can hear you. Yes, yes. Hello, Arsalan.
Yes, sir. Hello.
Yeah,
Okay, sir. I think so it's proper now.
can you hear me, Arsalan?
Yes, sir. I can. I can.
Yeah, yeah. So what I was saying is that the ideal scenario is that so it should be showing 1 ampere because the resistance is 3 ohm and then this is 3 voltage. So
Yes, sir.
the reading that we should be getting in the device that should be 1 ampere. But let's say that we are connecting directly. So case first, case first, directly connecting, directly connecting a galvanic. Right, so this is the first scenario. So we are connecting directly a galvanometer without any shunt resistance. This is the 3 ohm voltage This is the 3 ohm resistance. This is the 3 volt voltage, and then we are connecting a galvanometer which has some resistance, right? And what is the resistance of this galvanometer? That is what is so they have given 60 ohm, I guess. This is 60, right? So this device has its own resistance.
Yes, sir.
So then what is the total resistance that we are getting? Total resistance is
63.
63. 63 ohm resistance. Voltage is how much?
Voltage is 3 by 63.
3 volt. 3.
Oh, yes. Sorry, sir. Sorry. So I is equal to V
So
by
what
R.
would be
So,
the reading of current that we will be? Yeah. So
so
what is it? What is this
3 by
value?
63. So, yeah.
Value. So you see that 3 by 63 is
0.
0.047 ampere. So is this the ideal scenario?
No, sir. It should be 1 amp.
The, yeah, so the ideal scenario is that whatever device we are connecting, that should give 1 ampere reading. But
Yes.
so that is why. So this is the reason that we don't use the galvanometer directly, right? This is the exact way we measure the current because it has a high resistance. So that is why we shunt resistance. And then with this galvanometer, we connect a shunt resistance, right? And then we have this 3 ohm resistance. And then keyboard, this is how much? This is 3 ohm. This is resistance which is 60 ohm. This is shunt resistance. What was the value that they gave? We have connected here using which has this shunt resistance. And then this is connected to 3 ohm and then supply. Okay, so now let us check that what is the over. So what would be the R effective in this case? This would be 3 ohm. And then we have this R effective, and then this is so what is this R effective? These are in parallel. So R effective is for two parallel. This is the parallel connection, right? But for two connections, we can directly write this as R1 R2 divided by R1 plus R, right? So what is R1? R1 is RG and
Yes, sir.
R2 is S. So if we use these two things, so what we'll get?
So
60
16.02.
so 2 divided by 60 plus 0. So how much is this? 12. So this is 1 point, right?
Yes, sir.
And then divided by 60.0. So how much is this? R effective 1.2 divided by 1.2 divided by 60. So this is 0. 0.019. So we can write it as 0.0. This is R effect. Okay. Now, then what would be the reading that we will get? So now if we measure, so now the R equivalent, new, that would be how much? 3 plus R effective because these are in series, right? Then 3 plus
Yes, sir.
0.02. So this is the new effective resistance that we'll get. And voltage is 3 volt. So then what would be the current? This would be 3 by 3.0. What is this? 3 divided by 3.0. So 0.99, which is nearly to what? 0.99. How much is this? 0.99. That is 1.
One.
Right? So what did we see?
It's an
We
ideal.
saw, yeah, so this is nearly to the ideal case.
Yes,
This
and
is
yeah.
the this is the reading that we expected, right? So that is why this clears our answer. So that is why this question is very important. That why don't we use galvanometer directly? So the answer is that the galvanometer has a very high resistance. This is first reason. Second reason is that we will not get the reading of current correctly, right? So these are the two main reasons that we don't use directly galvanometer as the habit. We connect uh, resistance parallel to it, which is called a shunt resistance, and this has a very low value so that we reach the ideal case. Clear, sir?
Yes, sir.
Yes, then please note down this question. That is why this question is very, very, very important. And that's this beautifully explains the scenario, right?
Yes, sir.
Yeah, please note down this. Yeah, whenever want me to scroll down the script.
Yes, it is a good news. Yes, sir. Done.
Then, okay, so what about these portions. Got it?
Wait, I'll just note down the equation.
Yeah. Please.
Yes, sir, done.
Yeah. So this chapter is over there. Now let us go to chapter 6. Electromagnetic induction. And the first thing that we'll talk about is the magnetic flux. Okay, and we'll take the analogy from right. We'll take the analogy from electric. Yeah. So what is the flux? Electric flux? Do you remember? What is the electric flux? What happened to this thing? Can you hear me, Archana? Can you hear?
Yes, sir.
Yeah. So what was the electric flux? Do you remember? What was the electric flux?
Sir, electric flux. Yeah, yes, sir. I remember it a bit basically a bunch of electric field lines and like passing through like a certain area or a given area,
Yeah.
essentially.
Yes. That is exactly the electric flux. So the number of electric field lines passing normally. This is a very important word. Normally through the surface, right?
Yes, sir.
So that is called the electric flux. Happening. Let me just yeah. So electric flux was E dot A, right? Which was EA cos theta, right? This was electric flux. And if we take the analogy from this thing, what can you say about magnetic flux? What would be magnetic flux? Yes,
So
please.
magnetic field lines passing through like a given area.
Yeah.
Normal.
So the number of magnetic field lines passing normally surface, right? So this is what we call the magnetic flux. And so this is again taking the analogy from electric flux. What kind of quantity is this? What kind of quantity is this?
Yes, sir.
What kind of quantity is scalar or vector? Yes, what kind of
Uh,
quantity is this?
quantity like scalar and vector, sir. So vector, right? Magnetic flux because both
Vector.
direction and magnitude.
Okay, so what was the electric flux was what quantity? What quantity was the electric flux?
So that was scalar.
That was scalar. So this is also magnetic flux. What would be? Yes, it is also a scalar quantity, right?
Oh yes,
It's a
it's
scalar,
also a scalar quantity.
right? And how do we write? This is V dot E, right? Which is VA cos theta, where P is magnetic field, A is the area, and theta is the angle between the area vector and magnetic field. This is very important. If I ask you that, let's say if this is the surface, this is the surface. So what is the direction of area vector? Do you remember what is the direction?
So it's a direction of what?
Area vector. What is the direction of area vector? Yeah, what is the direction of area vector?
Sir, I'm not sure. Area vector.
Okay, so let's say you have this thing. The area is this portion, right? Right?
Yes, sir.
So the direction of area is perpendicular to this. If you have this thing, this is your area. So perpendicular normal to this thing, that is the direction of area vector. So if you have this area, so normal to this thing, that is the direction of, it's called n hat, direction of area vector. So if you have your screen, you're looking at some screen, right? So that screen and perpendicular normal ray, that screen will represent the direction of the area, right? So this is the direction of area vector.
Yes, sir.
Clear? And then
Yes,
the
sir.
last,
Perpendicular.
yeah, so direction of area vector, normal to the surface, normal
Hmm.
to the surface. That is how you denote the direction of the area, right? And then
Yes, sir.
the SI unit of magnetic flux is Weber, and this is represented as W. Right. These are the important things to remember about magnetic flux. And yeah, and you please note this thing down, and then we'll talk about the other.
Yes, sir.
Even you have Yeah, whenever you have noted it down, please.
Yes, sir. Done.
Yeah, one moment.
Yes, sir. Done.
Yeah, one. So the next thing is right. You practice some questions from this thing. Right. So in those kind of questions, you will be given the magnetic field, and then you will also be given the area vectors. Let me check if you. Question is that magnetic field magnetic field in space is given as I plus J plus 5K cos, and the surface is surface area of the material is as I plus 2J plus K, which is square. Find the magnetic flux passing. So yeah, please calculate this question and tell me what would be the answer. Okay, please first you calculate and then yes, did you get any answers?
Which I'm just starting on right now, sir.
Yes, please calculate it.
Mm.
Yes, did you get the answer?
Yes, sir.
Yeah,
So since it's A into B, right? With the magnetic flux.
yes. Magnetic flux is simply dot
A, yeah, yes, sir. Essentially that.
what we,
So 3i plus 2j plus 3k into 2i plus 3j plus 5k.
that is correct. Then what would be the answer that you will be getting? Yeah. So then what is the answer that you get?
So 3 into 2 is 6 plus 6 plus
Yeah.
15. So 6 plus 6 plus 15.
Yes. So this would be 12 and
12,
20. That is
27.
27 Weber. Right.
Yes,
Good.
sir.
So this would be the magnetic flux. This is correct. Why were you hesitating so much? This
No,
is
sir, I
correct.
thought I was wrong because
No,
I
no, no.
got it easily right. So I thought I did something wrong.
So if this is easy, this doesn't mean that you are wrong, right? So have some confidence. Right?
No,
That is
sir, just
that is a
I
yeah.
just got it much quicker than I thought. So I thought I did something wrong because I
No,
thought
no.
there was some huge step I was missing and might have
Yeah.
jumped into conclusion. So that's why I kind of hesitated.
No, no. So yeah, this is absolutely correct. Good. Okay, so this is about the magnetic flux. And then next one is the Gauss law for magnetic field. Again, we'll take the analogy for from the electric field. What was the Gauss law for electric field? Do you remember? What was the Gauss law?
So Gauss law for magnetic field, so it's that one, right? Uh, with Gauss.
Gauss law for electric field was E dot ds is the closed surface integral Q enclosed upon epsilon. Right. So flux was right. This was
Yes,
the
sir.
Gauss law, and it gave us the charge. Right. It gave us the charge. So similarly, we have Gauss law for magnetic field. So we have, let's say, this. We have this material, and the electric field lines are going outwards from it. Right. Or let's say we already have studied about the solenoids, or we have already studied about the bar. Right. Let's say this is North Pole, this is South Pole. So this goes from North Pole comes into the South. Right. And similarly, right. So the magnetic field lines comes from the North Pole and then goes into the South Pole. So if we consider, right, if we consider a loop, then in this surface integral, so the total number of outgoing is equal to the number of incoming. So flux would be zero, right? So this says that v dot ds in a closed integral that is zero, right? And if we compare this with qm, where this is the magnetic charge, right? And let's say this is some mu naught, right? So if this zero, then qm would be how much? This is Gauss law for magnetic. What does it say? That qm is zero, right? So it suggests that magnetic charge, which is also called monopole, does not exist, right? You have electric charge, so charge can be positive or negative. Do you have any material which has only positive magnetic field? Do you have any material? Yes.
Yes, sir.
Do you have any material which has only positive magnetic field?
Sir, magnetic bar with only true north.
So magnetic bar has two norths. Which magnetic bar has two
Only
norths?
north, sir. Only north, sir. Just cut it in half.
Okay, so if you have this magnetic bar and if you cut it in half, so you'll get only the north part.
Yes, sir.
So
Maybe according to my theory.
no, so again you will get, so this part will have south and this part will have north. So again you will get north and south and north. So again you will get north. So you cannot construct a magnet which has only one charge, one polarity. So this Gauss law says that magnetic monopole does not exist. So this is the idea. Is it clear? Is it clear? Yes. So
Yes.
this, yeah. So quickly note it down, and then we'll talk about the important one, which is the Faraday's law. So quickly note it down.
Yes, sir. I have a test today at 8 o'clock, sir.
Oh,
Yes, sir. Can you just give me last 10 minutes to just prepare for the test? I just want to revise it.
last 10 minutes. Okay, so we have 10 minutes, right? So after 10 minutes, I will stop. Okay.
Okay, sir. Thank you.
Yeah, whenever you have noted it down.
Yes, sir. Wait. I'll just write the one more line, sir. Let's finish that.
Yes, yes.
Yes, sir, done.
Yeah. Okay. So then the next thing that we have to study is the Faraday. What do you have? Yeah. So what is Faraday? Right. So Faraday experimented, and what did he do? That he he made a coil, right? Let's say this is one coil, and this was connected with some battery, and then this was another one. So these two coils are there, and then he moved this coil in this direction, right? Because some current was flowing in this thing. So due to this current, some magnetic flux was passing through this area, right? And then and then he connected a galvanometer through this thing, right? So when he moved this thing, then the galvanometer showed some deflection. So this was the idea. So what was happening is that because this is some current, and due to this current, there is a flux which is passing through this whole coil. And if we are moving this coil in this side, or we can also do this experiment as well. So we have this coil, and then we have this bar magnet. So what we can do is that we move this bar magnet to this side. And this, let's say that this we connect a galvanometer to this. So again, we will see a deflection in this one, right, due to the movement of this magnetic field. So let's say this is north and south. So, so due to these experiments, Faraday formulated that there would be a net EMF. Net EMF is created due change in flux, right? And what did he give? So he gave that this EMF would be directly proportional to the change in the flux, magnetic flux. And if we remove this thing, so we'll get this is n, and this is minus n d phi by dt, right? This would be if there are only one term, so this would be only minus d phi by dt for one term, and this is for n terms. Faraday that when we change the magnetic flux, so it will create an EMF, right? And and uh, and this minus sign is very important, justified by the conservation of energy. So this Lenz law is very important. This negative show that energy. So energy cannot come out of here. It only transferred, or it cannot be created or be split, right, from the energy consumption, right? So we already know that what is this phi? What is this phi? So this magnetic flux is Va cos theta, right? So if we put this value in here, so what we'll get minus n d by d. So there are three ways in which changing magnetic field, keeping A and theta constant, keeping B and keeping B and A constant. Or so where have you seen this scenario? Yes, Archala. So where have you seen this scenario? This is the scenario of AC generator. So in AC generator, we rotate it, so we change the theta, but magnetic field and area is constant. So we keep the area and magnetic field constant, only this theta is changed. So that is the working principle of AC generator. Quickly note it down and then we'll stop. Right, so you just note down this is what we call Faraday. Yeah, please note it down and then we'll stop it.
Yes, sir, done.